This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today we'll be delving into the archive paper DL Former, Enhancing Explainability in Multivariate Time Series Forecasting Using Distributed Lag Embedding. This paper tackles a crucial challenge in time series forecasting, balancing high prediction accuracy with interpretability. Let's start with the core problem. Why is explainability so important, especially in multivariate time series forecasting?
In many real-world applications, particularly in finance and healthcare, high prediction accuracy isn't enough. We need to understand why a model makes a specific prediction. This is especially true in multivariate settings where numerous interacting variables influence the outcome. Lack of explainability can hinder trust, limit debugging capabilities, and prevent the identification of potential biases or flaws in the model.
Traditional statistical methods like ARDL models offer some degree of interpretability, but they often struggle with the complexity of real-world data. How does DL Former address this limitation while maintaining competitive predictive performance?
DL Former leverages the power of attention-based models, specifically transformers, which are known for their ability to capture complex temporal dependencies. However, standard attention mechanisms often obscure the individual contributions of each variable. DL Former introduces distributed lagged embedding, DLE, to explicitly model the temporal influence of each variable independently. This allows us to disentangle the effects of different variables over time.
Can you elaborate on the distributed lag embedding DLE technique? How does it differ from the way traditional attention mechanisms handle temporal dependencies?
Traditional attention mechanisms often embed all variables together, making it difficult to isolate the impact of a single variable's past values. DLE, on the other hand, creates separate embeddings for the lagged values of each variable. This allows the model to learn the individual temporal dynamics of each variable and how they contribute to the overall forecast. We further enhance this by incorporating positional embeddings to capture the order of the lagged values.
The paper mentions interpretable multi-head attention. How does this contribute to the explainability of DL Former?
The interpretable multi-head attention mechanism allows us to analyze the attention weights for each head separately. This provides insights into which variables and time steps are most influential for each head's contribution to the final prediction. By averaging the attention weights across heads, we obtain a more robust and comprehensive representation of the variable importance.
The paper compares DL Former to several state-of-the-art models, including Informer, Autoformer, TFT, and TACN. What were the key findings of this comparison?
DL Former demonstrated comparable predictive performance to the leading attention-based models, Informer and Autoformer, across multiple datasets. Importantly, it significantly outperformed the existing interpretable models, TFT and TACN, in terms of both accuracy and the clarity of its explanations. This shows that we can achieve high accuracy without sacrificing interpretability.
The paper highlights explainability from both sequence and feature perspectives. Can you elaborate on how DL Former provides these insights?
From a sequence perspective, DL Former reveals the temporal influence of each variable on the prediction. We can visualize how the past values of each variable contribute to the forecast at each time step. From a feature perspective, DL Former identifies the overall importance of each variable in the prediction process. This allows us to understand which variables are most influential in driving the overall forecast.
The choice of the lag parameter L seems crucial in DL Former. How sensitive is the model's performance to this parameter? Did you explore different values of L?
Yes, we systematically explored different values of L. We found that the optimal value of L varied depending on the dataset and the forecasting horizon. Some datasets benefited from longer lags, capturing long-term dependencies, while others performed better with shorter lags. This highlights the importance of carefully selecting this hyperparameter based on the specific characteristics of the data.
The paper uses several evaluation metrics, including RMSE, R-squared, and DTW. Why were these chosen, and what do they tell us about DL Former's performance?
RMSE and R-squared are standard metrics for evaluating forecasting accuracy. RMSE measures the average prediction error, while R-squared indicates the proportion of variance explained by the model. DTW, dynamic time warping, is particularly useful for time series data because it accounts for potential shifts and distortions in the time axis. The combination of these metrics provides a comprehensive assessment of DL Former's predictive capabilities.
What are the limitations of DL Former, and what are some potential avenues for future research?
One limitation is the computational costs associated with handling long input sequences. Future research could focus on developing more efficient architectures or techniques to reduce this cost. Another area for improvement is exploring alternative methods for incorporating positional information into the DLE. Finally, extending DL Former to handle more complex data types such as irregular or missing data would be valuable.
The paper mentions the use of the atom optimizer and MSE loss function. Were these choices motivated by specific considerations, or were they standard choices for this type of problem?
While Atom is a popular and effective optimizer, and MSE is a common loss function for regression tasks, the choices were not arbitrary. Atom's adaptive learning rates are well suited for handling the complexities of deep learning models, and MSE provides a straightforward measure of prediction error. However, exploring alternative optimizers and loss functions could be a subject of future research.
The paper emphasizes the importance of explainability in AI. How does DL Former contribute to the broader field of explainable AI?
DL Former makes a significant contribution to XAI by providing a practical and effective method for enhancing the interpretability of multivariate time series forecasting models. It demonstrates that high accuracy and explainability are not mutually exclusive goals. The techniques used in DL Former, such as DLE and interpretable multi-head attention, could potentially inspire the development of more explainable models in other domains.
The paper mentions the use of ReLU activation functions. What is the rationale behind this choice, and are there any alternatives that might be worth exploring?
ReLU, rectified linear unit, is a popular choice for activation functions due to its simplicity and effectiveness in preventing the vanishing gradient problem. However, other activation functions such as leaky ReLU or ELU might offer advantages in certain situations. Exploring these alternatives could be a subject of future research to potentially improve the model's performance or robustness.
In summary, DL Former offers a compelling approach to multivariate time series forecasting by effectively balancing predictive accuracy with explainability. Its innovative use of DLE and interpretable multi-head attention provides valuable insights into the complex relationships between variables and their temporal dynamics. Thank you for this insightful discussion.